Welcome back to our ongoing deep dive into cooperative AI notes. This is number 5.
Episode 5, yeah.
And for you, the learner, especially if you're looking at, building safer AI, today we're aiming for that high-level view, sort of a TLDR on cooperative intelligence, building on what we've done.
Absolutely. It's good to pull back sometimes. So just a quick rewind for everyone.
Yeah, good idea.
We started way back with game theory, right? The basic rules of strategy.
Yep. Episode 1, then reinforcement learning.
How agents learn from rewards, trial and error, that was 2.
Episode 3 got serious with AI safety, super important stuff about alignment and values.
Crucial. And then last time, number 4, we started dipping our toes right into cooperative AI itself.
Exactly. Just the intro. So we've got those foundations laid.
Mm-hmm.
Now, today, we're sort of zooming out, looking at the big picture. Cooperation, yeah, but also competition and all that messy stuff in between.
The mixed motives.
Yeah. And we'll touch on why, maybe counterintuitively, understanding us, humans, might be key.
Yeah.
And also how thinking about this as a complex system offers a different angle than maybe the classic way of looking at multiple AIs.
Okay, so where should we start? Maybe the basics of those system types.
Sounds good. Let's unpack that.
Okay, so broadly speaking, you can think about these multi-agent interactions in a few ways based on their goals. First up, purely cooperative systems.
All right, the team players.
Exactly. Everyone's pulling in the same direction. They share common goals. Think about like optimizing a factory floor or maybe coordinating disaster relief drones.
Mm-hmm.
Minimize cost, maximize efficiency together.
All for one.
Pretty much. Then flip side, competitive systems.
Okay, the adversaries.
Right. Goals are in conflict. My win is your loss, potentially. Agents are trying to maximize their own payoff, often leading to that Nash equilibrium concept we know from game theory.
Like chess AI or Go AI playing against each other. Or maybe capture the flag bots.
Perfect examples. One agent's success directly impacts the other negatively.
Okay, cooperative, competitive. But you mentioned a third way.
Yes, and this is where it gets, well, much more like the real world. Mixed motive systems.
Ah, the messy middle ground.
That's a good way to put it. It's a blend. Agents have some shared interests, but also some conflicting ones.
So they need to cooperate sometimes, but they might also be tempted to compete.
Precisely. And this structure often creates what we call social dilemmas.
Like the prisoner's dilemma.
Yep.
Or maybe managing shared resources, fishing stocks, clean air, that kind of thing.
Exactly that, where what's rational for one individual agent, maybe take a little extra, could actually lead to a worse outcome for everyone if everybody done it.
That tension, it feels very familiar.
It really is. Most real-world scenarios where multiple agents or people interact aren't purely win-win or win-lose, but this complex dance. Business negotiations, traffic, so much fits here.
Understanding how AI can navigate that complexity seems like a huge challenge then.
It's a central challenge, yeah. Recognizing that it's often not black and white, but shades of gray is key.
Okay, system types make sense. Cooperative, competitive, mixed. Now, this idea about human data, you hear so much about AI learning through self-play, right? Playing itself millions of times.
Mm-hmm.
Why bring messy, potentially flawed humans into it, especially if we want AI to be better than us?
That's the million-dollar question, isn't it? And self-play is incredibly powerful. Look at AlphaGo, AlphaZero.
Superhuman performance in complex games.
Absolutely. But those games, even complex ones, usually have very clear rules, very clear win-loss conditions or point systems. The reward is well-defined.
Okay.
The real world often doesn't work like that. Goals can be fuzzy, ill-defined. What does good collaboration on a team really mean in terms of a simple score? It's hard to pin down.
So an AI might master chess, but struggle to, co-write a report with a human effectively because effectiveness is subjective.
Yeah, you've got it. Self-play alone might not get us AI that aligns with nuanced human values or preferences in these less defined situations. We might end up with AI that's brilliant in its own simulation, but brittle or even unhelpful when interacting with us.
So human feedback provides what? A different kind of signal.
Yeah, it provides signals about what we consider desirable or helpful behavior, things that are hard to just program in as a reward function. It helps ground the AI's learning in, well, our reality.
Okay, that makes sense. What about trying to just copy humans? I think it's called behavioral cloning.
Right, behavioral cloning, that's another approach. You train the AI on lots of data showing how humans perform a task. Try to get the AI to mimic the human.
Sounds reasonable.
Maybe.
It can be useful, yeah, for getting AI to do things in a human-like way. but it has drawbacks.
Like what? Are we just teaching the AI our own mistakes and biases?
That's the big one, yes. It can overfit to human limitations. The AI learns our bad habits, our inefficiencies, right alongside the good stuff. It doesn't necessarily push the AI to find truly optimal or novel solutions. So pure imitation isn't the answer either. It's more subtle.
Much more subtle. We don't just want mimics. Maybe we want AI that understands the intent behind human actions in cooperative settings, but can improve upon the execution.
So if self-play has limits for real-world fuzziness and pure cloning copies our flaws, what's the way forward? Combining them.
That seems to be a really promising direction, yeah. Combining human data and self-play.
How would that work?
Well, you could use human data, maybe demonstrations or feedback, to give the AI a good starting point. Like, here's roughly what good looks like.
Okay, bootstrap the learning.
Exactly. And then let the AI use self-play or other reinforcement learning techniques to explore, refine, discover strategies that are even better, potentially beyond what humans currently do.
Like learning the basics from a teacher, then going off to do your own PhD research.
That's a nice analogy, yeah. Best of both worlds, hopefully. More grounded than pure self-play, more optimal than pure cloning.
Interesting. Okay, shifting gears slightly. The outline mentions this idea of a complex systems framing versus a more classical multi-agent view. What's the difference in perspective there?
Right. This is a useful distinction. The, let's call it the classical multi-agent systems MES perspective often really zooms in on the individual agents.
Okay, like what is Agent A trying to achieve? What's its best strategy given Agent B?
Exactly. It analyzes individual goals, strategies, and looks for equilibrium points, like that Nash equilibrium again. It draws heavily on game theory. What's the optimal rational move for each player?
So very bottom up, focused on the individual's decision calculus.
Pretty much. Now, the complex systems framing, it sort of flips the telescope around. It looks at the whole collection of agents interacting as, well, a complex system.
And less about the individual dancer, more about the patterns on the whole dance floor.
That's a great way to put it. It focuses more on the emergent behavior that arises from all those individual interactions. What are the overall system dynamics? Is the system stable? Does cooperation emerge spontaneously? It's a more top-down, holistic view sometimes.
Okay, so one looks at the trees, the other looks more at the forest and how it behaves overall.
Nicely summarized. And within these interactions, especially if explicit coordination isn't possible, modeling other agents becomes vital, wouldn't you say?
Absolutely. You need to have some idea of what the others are trying to do, right?
Yeah.
Or what they think you're trying to do.
Precisely. This isn't a new idea, of course. Game theory has tackled theory of mind concepts for ages. Early AI work had things like fictitious play.
Right, which is like learning by watching what others did before and assuming they'll keep doing it.
Sort of, yeah. Building a model based on past actions. But it's gotten much more sophisticated now. We have Bayesian methods trying to infer beliefs and goals.
Right.
Even recursive reasoning.
Recursive reasoning, like, I think that you think that I think.
Exactly, that kind of nested modeling. It can get complex fast, but it's crucial for sophisticated coordination or negotiation when you can't just talk things out. And of course, understanding others is only part of it. The environment they're all interacting in matters hugely.
Oh, for sure. Driving a car in traffic versus playing poker online. Totally different worlds.
Right. Is the environment fully observable? Does everyone see everything? Or only partially? Most real-world stuff is partial, right?
Yeah, you don't know exactly what other drivers are thinking or seeing.
And are actions discrete, like choosing move A or B, or continuous, like steering a wheel? Is the outcome of an action predictable, or is there randomness involved? All these environmental factors shape how agents learn and interact.
It adds so many layers of complexity.
It really does. And you touched on this, but communication. If agents can communicate in cooperative settings, that's obviously a massive advantage.
Yeah, seems like a shortcut to coordination.
Yeah.
How are researchers approaching AI communication? Are they just programming in languages?
Sometimes, but what's really exciting is work on learned communication protocol.
Learned. The AI figures out how to talk itself.
Kind of. Using techniques often called centralized training for decentralized execution. You train a team of agents together in simulation, allowing them to develop their own signals, their own language, purely based on what helps them achieve their shared goal better.
Wow. So they invent a communication system optimized for the task.
That's the idea. They figure out what information is crucial to share and how to encode it efficiently. Then, once trained, they can use that learned protocol out in the wild, executing decentrally.
That's That's pretty amazing, developing language from scratch based on need.
It's a fascinating area. And it leads to one final big challenge I want to mention, credit assignment.
Ah, okay. So the team wins,
Hmm.
but who gets the credit? Or the reward?
Exactly. If you have a shared team reward, how do you figure out which individual agent's actions were actually helpful and which maybe weren't or were even detrimental? It's tough.
Yeah, I can see that, especially if there are delays between actions and the final outcome.
Totally. And researchers are exploring lots of ways to tackle this. Things like trying to factorize the team value into individual contributions or using intrinsic rewards.
Intrinsic rewards, like
Ugh.
rewarding an agent just for exploring or doing something novel, even if it doesn't immediately lead to points.
Sort of, yeah. Rewarding agents for achieving sub-goals or demonstrating behaviors that are generally useful for cooperation, trying to encourage good local actions that contribute to the global good. It's a really active area.
Man, okay, so wrapping your head around cooperative AI involves understanding the game type, the potential need for human input, seeing the bigger system picture, how agents model each other, the environment's role, communication, and how to share the credit. That's a lot to juggle.
It absolutely is. It's a rich, multifaceted field, and we're really just scratching the surface.
But it feels like understanding these pieces is critical, especially for that goal of safe and beneficial AI.
I completely agree. And actually, that sets us up nicely for where we're going next.
Oh, yeah. What's in the next deep dive?
Well, having laid out this landscape, our next session on cooperative AI notes will zoom right in on some specific algorithms and techniques. How do we actually build systems that foster cooperation?
Okay, getting into the nuts and bolts.
Exactly. We'll look at things like counterfactual regret minimization. That's a cool way agents learn by thinking, what if I'd done something different? We'll dig deeper into different ways to solve that credit assignment puzzle and explore more about how intrinsic motivation, that internal drive, can help agents become better collaborators.
Awesome. So moving from the what and why more into the how.
Precisely. The cutting edge of actually engineering cooperative AI. Definitely something to look forward to.
Sounds great. Okay, well, that feels like a good place to pause our overview for today then. We've covered a fair bit of ground, giving that high-level view into cooperative intelligence.
Yeah, we unpacked the different system types, cooperative, competitive, mixed motive, talked about why human data might be more necessary than you'd think.
Right. And contrasted that classical agent view with the broader complex systems perspective.
Hopefully for you, the learner, especially if safety is top of mind, this gives a solid foundation. Maybe sparked a few aha moments without being too overwhelming.
We hope so. So maybe take a moment and think, what stood out for you from all that? What questions are still buzzing around?
Yeah, definitely encourage you to dig deeper into any parts that caught your interest.
And maybe here's just a final thought to leave you with.
Go for it.
As these AI systems get woven more and more into our daily lives, into our economies, our infrastructure, understanding these principles of cooperation, competition, alignment, figuring out how to design systems that encourage working together effectively, that feels absolutely essential, doesn't it, for navigating the very multi-agent future we seem to be heading into.
Couldn't agree more. It's not just theoretical anymore. It's becoming fundamentally practical.